So today we are finding domain and range of functions and then identifying the local max and min, as well as looking at function symmetry. So the first definition is a function maps every element in its domain to exactly one element in its range. So this is just a fancy way of saying that for every x you pick, there's only one y for that x. So like you don't have x equaling 2 going to x equals 2 and or y equals 2 and y equals 4. So you could say every x has only one y value. You probably will recall the vertical line test. This is the test you use to decide if something is a function or not. So if it does not pass the vertical line test, it is not a function. So getting into that, some examples here. So vertical line test is exactly like it sounds, draw a vertical line. If you hit the function more than once, or the graph more than once, then it's not a function. So this would be not a function. If we draw some lines here, we're only ever hitting once. So this one is a function. This one would also be a function. This one's a little tricky, but if I draw a line, no matter where I draw it, even if I draw it right here, I'm only ever hitting once. So this one is a function. The reason being, this is an open circle and this is a closed circle, so I'm technically only hitting the function once because there's only one value right there. All right, domains and ranges. So the domain is a set of all possible input values or all possible x's. So if you think of it on a graph, you're looking at what x values does your function hit. Does it only touch part of them? Does it touch all of them? Does it touch 2 to 5? Where are the x's on your graph? The range is then all possible output values or all possible y's or f of x's. So the domain you can often see just from the function. For the range, you want to graph it and look at the graph. But on a graph like this, you're looking at your y values right there. So let's do some examples. So if we're looking for the domain of G, we want to figure out what x values are you hitting. So looking at this, we're going off into infinity and off into infinity. So we're hitting everything on this list. So you're going from negative infinity to positive infinity. Here we want to use interval notation, which we talked about in the last video. So negative infinity is the smallest we get, positive infinity is the largest, reaching all the real numbers. Next, if we look at the range, you want to look at what y values is it hitting. So put that there. So if we're looking at this, our y values start right here. We don't go less than that, and then we keep going up to infinity. So we start at 0, and we include it, so we're going to do a square bracket, and then we go all the way to infinity because it doesn't stop, it just keeps going up. So that would be the domain and range here. Next example, if we're looking at the domain, we want to figure out, again, what x values are we talking about. So here we start x right there, and then we keep going because there's an arrow going on there. So we're going to start at 1, and we have a value right at 1, so we have a square bracket, and then we're going on to infinity. If we're looking at the range, get a different color, we want to figure out what y values are you touching. So looking at this, it looks like we start right here, and then we're going all the way down because there's an arrow right there. The question then is, do we include positive 6? If you look right here, it's an open circle. So we're going to have an open bracket at 6 because we don't actually include it. You never actually touch that value. And then we're going to negative infinity because we're going down. So how I wrote this is actually wrong. You're going to want to switch this because you don't want to put the smaller number last. So we're going to go back here, and we have negative infinity to positive 6. Kind of like you don't like write a sentence backwards. You don't start with a period. You want to do the smallest number going towards the biggest number. A note, you never, ever, 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 ever put a square bracket on infinity because you can't actually ever reach it. You could always find a bigger number and keep going. All right, some functions here. So we're going to find just the domain here. If you want, you can graph them after we figure it out, but you should be able to find the domain just by looking at it. So if you think of the function the square root of x, what would make it not work? Like what would make that function not possible? You can plug in any positive value. If you plug in a negative value, you're going to get an imaginary number. So the smallest number you can actually plug in that will work is going to be 0. And you can actually plug in 0. Square root of 0 is just 0. And then you can do any positive number. So your domain is going to be 0 to infinity. If you look at the graph, it's going to be something like this. So your range then would also be 0 to infinity. This next one is a little different. I'm going to simplify it first. So you can get 8x on top. And then the bottom, if you remember, is going to be able to be factored. So you'll get x minus 3x plus 3, since it's the difference of perfect squares. So looking at this, we want to figure out, well, what's going to make this not work? What's going to give me an undefined value? What's going to give me an error on the calculator? You can't divide by 0. So here, x can't equal plus or minus 3, because that would make the bottom 0. So how do you actually write that? So we can go any negative number all the way until we hit negative 3, but we can't include negative 3. So you want a parenthesis, but then we have more that we can actually include. So you want to do a union, and then we can go negative 3 to positive 3, and then 3 to infinity. So if I draw this out on a number line to give you kind of a visual, if this is your x-axis, right, we have negative 3 right here and positive 3 right here. We can't touch them. There's holes right there. We don't actually want to reach those values. So your interval then is going to be this chunk, but not touching negative 3, this chunk not touching negative 3, and this chunk not touching positive 3. So this corresponds to this part. Here corresponds to here. And this chunk corresponds to this chunk. So you're writing like the sections of your number line that you can use. Local maximum. This should be some review. So here we want to identify what are the local maximums and minimums. They're exactly what they sound like. So up here, that's going to be your maximum. You're going to write these as points. So the local maximum is at 3, 2. The local minimum then is wherever the low points are. So here and here. A note, the local just means that there can be more than one. If you had a global max or min, that would have to be the highest value all over or the lowest value all over. The local is just saying, well, where is there a low point? Where is there a high point? So your local minimums are at 0, negative 4, and 6, negative 8. Well, then where is it increasing and decreasing? So an interval is increasing when it's going up or your slope is positive. So this would be your increasing chunks. An interval means you want your x values. So on what x values is it increasing for your function? So right here we have 0, and then here we have 3. And note, you're going to have open parentheses here because you can't actually be increasing or decreasing at this point. If you're sitting right here, you're flat. You're not going up, you're not going down. You're just at like an equilibrium. So you're not increasing or decreasing. If we then look for decreasing, that's where you're going down. So it's those chunks. We're going to be going, oh, I forgot the second part of our increasing. Go back to that. Is this right here. So we are union with 6 to infinity because we keep going on with that arrow. So our interval of decreasing, we're coming from over here, this negative x value, so from negative infinity, we stop at 0, and then we start again at 3 and end at 6. So those would be your intervals. So then function symmetry. So a couple definitions here. An even function is a function that is symmetric about the y-axis. So you're looking at your y-axis here, and you want it to be the same on this side and the same on that side. So you can flip it over that y-axis and get a mirror image. So here's some examples. 2 of these are even and 1 is not. So you can see this one is an even function. If I draw a line right here, this is exactly the same as that side. I could flip it over and get the same one. This would also be an even function because I can flip over the y, get the same thing. This one right here, if I draw my y-axis, it's not the same. That does not look like that, so it can't be an even function. So look at this. What looks familiar for all of these are, why do you think it's called an even function? If you look here at their exponents, the even ones have even exponents. Here you have an odd exponent. So odd functions, these are symmetric about the origin. So if I go like that, these are going to be the same around this point. So here's some examples. Here's an odd function. So if we're looking at the origin, 1 goes up, 1 goes down. It's like we're flipping it over this point. Here again, same idea, we're flipping it over this point. So this is the same as over there, this is the same as over there, etc. This right here is not an odd function, so I put my point right there. We're not flipping over the origin. We're doing some stuff about right here at 2, but we're not going about the origin, so it's not an odd function. Why you would call it odd is if you look here, we have odd exponents, and then this one is not an odd function. So just a note, not all symmetrics about the y-axis are even, and not all functions are functions that are symmetric around. Let me say that again. So note here, all functions that are symmetric around the y-axis are even, and then all that are symmetric around the origin are odd, no matter what their exponents are. So that's not like a good indicator all the time. For example, your sine and cosine. So we want to decide is sine odd, even, or neither. If we're looking at this, it's obviously not a flip across the y-axis because then we'd have a hump up here. But it is the same about the origin. So this is an odd function. Here if we draw our y-axis, we're flipping over that, and we have an even function for sine, for cosine. So even though there's no exponents, you can have an odd and even function. Here's your assignment. It should also be on Schoology. Let me know if you have any questions.